Good morning everyone. We're here to talk about our system, Verifiable Decentralized Computing Resource Sharing System. My colleagues are Amr Gouhar, Ahmed Ghazy, Ahmed Ibrahim, George Youssef and myself, Mohamed Ahmed. Our project is supervised by Dr. Sherif El-Kassas and Dr. Karim Sobh. Firstly, let's revisit our problem where Alice wants to outsource the computation of a function on a network of workers where she needs to receive a proof of correctness that doesn't require much work from the worker to do and doesn't require much work from the user to verify. The motivation behind our idea is creating a system that would allow the execution of a very high loads of computation without the need of the user to be computationally strong, all done in a decentralized environment, such that there are neither a governmental supervising entity nor exists a single point of failure, such that the computations are private and the execution has a proof of correctness. In other words, all computations are verified within the system without the user having to impose or do any type of verification on his part. Let's start by revisiting Gauss garbled circuits construction and our slight modification in it to suit the purpose of free randomization. This protocol is used to outsource the functions for evaluation securely and with a proof of correctness. This process starts with generating the Boolean circuit equivalent to the function. Then, using a random seed, each bit in the resulting truth table of the circuit would be replaced with a random ciphertext. Then, those ciphertexts will be used to generate the garbled values by multiplying the ciphertexts of each entry and using the result as a key to encrypt the output label. To later evaluate the garbled circuit, we will use the ciphertexts corresponding to the input wires in the same entry. We will multiply them and generate the key, and then loop over the table garbled values and try to decrypt each entry until one finally unlocks, and this would be the true result of the evaluation. Let's recall an nth construction, which is the base model that we base our system on and modified. We have one client wanting to outsource a computation and n servers to help him execute his computation. First, the client would generate a randomization seeds used to generate the input and the output wires for the garbled circuit without generating the actual garbled circuit, just its input and output wires. Then the client will re-randomize those wires, generating new forms corresponding to each garbled circuit from GC2 to GCN-1 using the generated seeds. Finally, he would construct a message array. Each index would contain the randomization seed to each server encrypted using the public key of that respective server. The final message includes the input values to garbled circuit GCN-1. The first server would receive the message array from the client, extract his message and decrypt it with his private key. Then garbles the function if, then he appends the generated GC1 to the array and forwards it to the next server. Servers from 2 to n-1 would receive the array and decrypt their messages and re-randomize the garbled circuit received from the previous server to generate a new garbled circuit, which is the equivalent to the first one but indistinguishable from it. Then he'd append his generated GC to the array and encrypt it with the next server's public key and forwards the array. Server N receives the message array and extracts his messages, the re-randomized garbled circuit received from server N-1 and the input wires received from the client. Then he evaluates the circuit and forwards the result to the client. The client finally receives back the evaluation result from server N. He then verifies it's a valid output wire from the set he generated earlier. The client will then decode the wire by finding its corresponding bit value.
So now that we have reviewed the problem and the background, let's continue to our research contributions. VDCS, our system, offers the following: verifiability through using Gauss garbled circuits, decentralization through using a blockchain to handle communication, and so computing resources could be shared. It also ensures privacy and security of the input and output because we are using gamma encryption and re-randomization. More on that later. However, we drop the privacy of the function because we will have a repo of circuits. Despite all of this, our implementation is not efficient. However, this was not an objective of ours from the start. Moving on to our encryption scheme, we are using El-Gamal, which is an asymmetric public key encryption scheme that is useful for our purposes. This is because it is secure against all passive attacks, meaning that no one can decrypt the message without having the private key, which requires solving the discrete log problem. So far, there is no efficient solution for this problem for correctly chosen parameters. Furthermore, it is homomorphic under multiplication, which means we can re-randomize ciphertexts without decrypting them. The scheme is simple. Basically, the server will have a private key X and a public key consisting of a large prime number P, a generator G for the multiplicative group ZP, and Y, which equals G power X. The client encrypts the message M by computing two values, G power K and M multiplied by Y power K, all mod P, where K is a random number. The server can decrypt by dividing the second value over the first value raised to the power of the private key. Thus, as shown in the slide, it will result in finding the value of M. Now that our encryption scheme is clear, we can move on to understand our re-randomization scheme. Our goal is, upon receiving a garbled circuit, the re-randomizing server should change the value of encrypted label Z and change the private key of encryption X without knowing any of them, and the result should be an equivalent garbled circuit. The input to our algorithm is the garbled circuit, which is pairs of C1 and C2 values resulting from encrypting the label Z under El-Gamal using the private key X. Also, it receives a random seed S provided by the client. The algorithm goes as follows. First, the server computes a random value R using the seed S. Then it computes a new public key which is the same as the old one except that Y is changed to Y power R. Then it computes the modular rth root of C1 and multiplies C2 by R, which will result in the shown values for the new pair. Simply, G power K over R and Z multiplied by R multiplied by G power XK. Then the encryption of 1 is computed using the new public key, which will result in the pair G power small r and G power XR small r. Then the pairs resulting from the previous steps are multiplied to have the new circuit, which is going to be G power small r plus K over R and Z multiplied by R multiplied by G power XK plus XR small r. The claim is that this new circuit is equivalent to the old one if the old one is encrypted under the private key XR and the labels are equal to ZR. This could be verified by decrypting the new circuit, which will result in the label ZR, as shown in the slides. We were faced with the problem of modular rth roots. However, due to the fact that we cannot find an efficient solution for this problem, we decided that we will use certain values of R that have the property that GCD of R and P minus 1 is 1, because modular roots are easy and efficient to find for those R's. It does not compromise security because according to the Euler-Tishent function, the number of integers that are relatively prime to a prime number P and are less than P is equal to P minus 1. P minus 1 is not guaranteed to be prime, however, P is guaranteed to be a very large prime, which means that even if the Euler-Tishent function of P minus 1 results in a value less than that of the function evaluated for P, the number of integers R is still going to be large enough to ensure security. And now, George will continue with the rest of our research contributions.
So we adopted the enhanced one client and server construction as we said. Then we thought that we could reduce the communication overhead of the final server that sends back the garbled circuit to the client. This was resolved by having the cycle complete the same way as the original model. However, initially the array of messages wouldn't have the input wires. But once server N receives the array of messages, he would wait for the client to send the input wires he wishes to evaluate the circuit on. So now the whole pass from the client to the evaluating server could be done in parallel for each request. We modified the way the original construction used to encrypt the message array. After each message is constructed, the client will encrypt it using a randomly generated symmetric key. Then this key will be encrypted using a public key of server I. Now array of messages and array of symmetric keys will be sent to the servers. We did it to make space for the fault tolerance later. When a server is down during the execution, we wouldn't have to reconstruct the message, only the corresponding symmetric key, as it will be encrypted with the public key of the new server entering the cycle. In order to achieve decentralization in the communication channel between all nodes, we propose that the whole system be a blockchain system where network nodes are the servers, clients, miners, and validators. Any node can act as one or all of those. This construction should facilitate the payment after the cycle is complete and guarantee the anonymity and privacy of the clients as well as the servers. However, because of timing constraints and the many other goals we were pursuing, we didn't investigate this proposal in details and left it open in the research paper for future work. As a quick overview of our prototype, we have a client and a set of servers. Each one of them will register on the directory of service. The client will request a cycle from the directory, which in return will reply with the cycle. Then the client will construct and encrypt an array of messages, as discussed previously, and forward it to the first server, which will do garbling. Then the first server will append the garbled circuit to the array and send it to the following server, which will re-randomize the garbled circuit and forward it, and so on until we reach the last server, which will wait until the client sends the input wires to evaluate the circuit. After that, the circuit will be evaluated and sent back to the client for verification. And now Amr Gouhar will continue.
So now to the implementation part. What have we done aside from our research contributions that we've discussed so far in the presentation? Our implementation is a proof of concept prototype to show an example of the system construction that we propose in the paper. It is composed of 4 main components that we'll go through one by one: the VDCS library, server nodes, preprocessor client nodes, and finally the directory of service implemented on a blockchain. Let's begin with the VDCS library. The VDCS library is the core of our implementation. It is used by all the nodes to do their functions. It includes implementations of some general functions such as encryption, decryption, information setters and getters, and many other utility functions used throughout our system. The second category of functions is the client-specific functions, such as the message array generation and encryption functions to generate the randomness and to generate the input-output wires and re-randomize them, and many other functions that are only used by the client nodes. The third category includes functions used only by the server, such as the garble, rerand, evaluate, and message array decryption functions. The fourth and final category includes the communication functions to invoke the different actions in the blockchain contract and communicate with the different nodes, whether they are client or server nodes. We kept the functions responsible for communication with the central DS, and there is a flag set by the method of registration to signal the use of one mode over the other to ease the process of any future development. The second component is the server nodes. The server nodes are multi-threaded nodes capable of handling multiple requests of the same or different types at the same time. They use the VDCS to register in the DS contract and communicate with the other nodes, as we said in a previous slide. The flow of each request received goes as follows. The server extracts the message from the array and decrypts the message type, and based on the type it opens a thread with one of the following scenarios. First, garble logic. It garbles the circuit sent by the client after decryption, and it sends it with the message array to the following server. Second, re-randomize logic. It re-randomizes the garbled circuit sent by the previous server and forwards it with the message array to the next server. For the evaluate logic, the request is either sent by a client or a server. The first one to arrive waits in a queue until its pair arrives. Then the garbled circuit sent by the previous server would be evaluated using the input wires sent by the client. Then the resulting output wires would be sent back to the client. The third component is the preprocessor. There are many reasons behind the preprocessor. First is to showcase the advantage of having a part of the cycle execution parallelizable, and this is done by generating multiple threads at the beginning of the code to request computations, so the first part of the cycle would be done in parallel, while the evaluations will be done sequentially as the order of code dictates. Another benefit is hybrid code execution. We found that it will be useful to outsource only needed parts of the code. while executing the rest of the code on the client's machine. So it will be a hybrid execution. This implies the need of a preprocessor whose main function is to identify the parts of the code which the user wants to outsource. The preprocessor now supports the outsourcing of regular statements, if statements, as well as constant loops. This methodology reduced the cost of computation request since we are only outsourcing small parts of the code instead of the entire code. This also gives the value of added privacy because no server will know the entire code of the circuit of the client, but just an operation from it. Moreover, the Boolean circuits will be constructed quickly since we will have a set of supported operations for which the Boolean circuits will be known. So there will be no need to worry about this complexity of this part, especially that the Boolean circuits will be written in a JSON format, which is easy for the client to produce. The preprocessor processes simple front-end and syntax that works independent of the code it's joined with, while the back-end still generates runnable Golang code that allows the client to do all what we've mentioned so far. And now Ahmed Ghazy will continue with our fourth component.
So our fourth component is basically our infrastructure based on the AUC blockchain in order to achieve decentralization, as my colleague George has mentioned earlier. It uses an underlying proof-of-stake algorithm, which makes it attractive for us to use, being lightweight and not requiring much processing power from the nodes. AUC has a growing and supportive community. Their APIs were well documented, which made it easy for us to deploy our directory of service contract, offering the two main actions of first, registration, in which a node records its communication information and announces its so-called processing power, represented as the number of gates it's offering to evaluate. Then there is a second action of fetching a cycle of end servers to be used by the client. And then here is a security parameter, so a longer cycle means higher probability of satisfying the honest server assumption. So before moving on to the demo, here is a brief summary of the major takeaways of our work. On the theoretical side, our contributions can be summarized in the following set of points. First, we describe a simpler, more efficient variant of a protocol for delegating verifiable computations that simplifies and follows up on the work of Anand et al. This is made possible by using an alternative construction of Yau's garbled circuits based on L-gamma encryption versus the more complex PHHO used in the original work. This let us reduce the complexity of re-randomization, for example, to a simple multiplication of integers. In our construction, we have used techniques from Gentry et al. As well as Mironov et al. Of course, subtleties and incompatibilities arise trying to combine points A and B without compromising security and privacy. So we had to solve them on our own, often making use of the honest server assumption. We outlined the protocol, the alternative garbled circuits construction, and our proposed solutions to subtleties in our research paper, which we have completed the first draft of and are working to restructure things for a second draft by the final submission. On the applied side, we have used the ideas we developed to implement a decentralized system that lives up to the security and privacy expectations, but does suffer performance issues as mentioned in the beginning. We describe our system design and architecture in our final technical report. And now we can move on to our demo of the current implementation. So here's an example of how a client might make use of our system by embedding a code like the one you see in their own application. This one in particular does 100 single byte comparisons followed by a comparison of two 16 kilobit strings that differ only in a single bit, as you see, and then prints out the result. And there are several reasons a user might want to do that. One of them is keeping their very top secret array of bees private, as well as the result of some computation away from a cloud. Another reason is also simply lacking the resources to do it, which is around 4 kilobytes of RAM in this example, as well as being very error sensitive. And now let's run the script through our preprocessor to produce the client.go Golang file that we're going to run in a moment. And as you can see, here it is, produced. Here is a side-by-side comparison of the input versus output. The Golang file includes the necessary libraries, invokes the registration action on top of the blockchain, starts the HTTP client, starts the threaded communication channels, and here's the user program that more closely resembles the one on the right, except for the loop being unrolled with the correct parameters. Here's the last segment of the code, comparing the two 16 kilobit strings and printing out the result. This eval stub is taken from the VDCS library for 2 string operands. Here's a view of the locally deployed contract on top of the AUC blockchain with a blank user table, ready to receive registration requests from the servers that go up right now. As you can see, 4 servers registered successfully, announcing their processing power of 32,000 gates, ready to receive the client request, who's now gonna run the client.go Golang file that we generated a moment ago. As you can see, the client is already receiving the evaluation results for the 100 comparisons. So let's speed up through that. And as you can see in the background, garbling the larger example is already being done in parallel. And finally, we're through the 100 comparisons and pending the result of the last 16 kilobit comparisons. And finally, we have received the result, which is false, and this took 16 minutes. But remember that each of these evaluations required a cycle of 4 servers, but as you can see, there are only 4 servers in the demo, which puts them under very heavy load. So in a more lively setting, a more efficient distinct cycles would be created, basically balancing the loads between them and increasing efficiency. Also note that all of these nodes are running a large number of threads, all of them competing for CPU time on my machine, since I'm the one playing the roles of the client and the server. And that was it for our demo. So thank you for listening, and do you have any questions?